like to thank the organizers for giving me the opportunity, for inviting me to this very interesting workshop, and I had very interesting visits and discussions already. I will present you a little bit now on work on frequency metrology on optical clocks. So I am from PTB, which is Germany's National Metrology Institute. So one could say the equivalent of NIST in Germany. Although PTB is even older, it was founded in 1880 already. I'm with the Time and Frequency Department. We have a broad range of activities and duties, but today I'm going to speak about our research work on optical clocks, specifically on trapped ion optical clocks. And I will speak a little bit about the scientific application of these clocks in terms of testing fundamental principles of physics, testing the validity of Einstein's equivalence principle. So in this sense, the motivation for our work on clocks is really, there is two main interests. So the one, of course, is fundamental metrology. This is our task to provide a very precise realization of the base units, of the unit of time in this sense. So we are working on cesium fountains, and we are also working on optical clocks, because we expect them to be the next generation of primary clocks that will realize the SI base unit in the future. But I think it's very interesting, and it goes very much hand in hand, that in the development of these new and very precise clocks, we can do interesting tests of fundamental questions of physics, and this is what one may call search for new physics. So effects that are not really quantitatively predicted, but that are motivated by rather generic ideas of bringing quantum theory together with theory of gravitation, with general relativity, and the theories that are developed to fulfill this unification of quantum theory and of relativity. They predict a number of violations of the equivalence principle, and it would be, of course, very interesting to do high precision experiments to find such new effects. You can see it's a little bit of a frontier towards new physics, but not at high energies or so, but at the high precision front. There is a very nice review article on this field by Mariana Safronova and colleagues appeared last year in Review of Modern Physics, Search for New Physics with Atoms and Molecules, and they are very nicely summarizing these ideas. I'm just going to speak about one example, which was, we did a clock comparison to check the validity of Lorentz symmetry with the clocks. So atomic clocks have developed enormously over the last 2 decades, mainly by the introduction of the methods of laser cooling that provides the slow atoms and reduces the Doppler shifts, and by trapping that provides the localization of the atoms. And using these two methods, cooling and trapping, is relevant for all the modern atomic clocks that are used. So there's the most precise realization of the SI second is a cesium fountain clock where laser cooling is performed to produce a sample of very cold cesium atoms at a microkelvin temperature. And then these are thrown upwards against gravity and on the free parabolic flight. The microwave resonance is interrogated and the cesium resonance frequency is determined. Optical clocks are also trapping the atoms, so there is two main systems that are investigated. So either neutral atoms are investigated that can be trapped in optical lattices, interference patterns of red detuned laser beams, like here in 1 dimension, a standing wave, or in 2 dimension, these 2-dimensional patterns. These traps are detuned so that the wavelength of this type of trap is chosen so that it does not perturb the frequency of the reference transition that should be used for the clock. This is called the magic wavelength. And then it can interrogate very many atoms at the same time, trapped in individual traps. My group is mainly working on trapped ions. So with trapped ions, there is the advantage that one has the charge of the atom as an additional handle that allows to confine the ion in a way that does not perturb the level structure, the internal level structure, and so it is a very nice system for high precision spectroscopy and eventually for clocks. So this is a type of ion traps we are using. It's about 1 millimeter structure, 3 electrodes, providing an electric quadrupole potential. And then these ions are also laser cooled, and you can see they form, if there is like 5 ions in this case in the trap, they form what we call a Coulomb crystal. So the ions are compressed by the trap, they repel each other, and at the millikelvin temperature or so that we have here, they form this equilibrium structure. For the, I will show you in a minute, for the precision work, we are actually not looking at 5 ions, but actually at a single one, because the central one is the one that has the smallest perturbation. If you would like to go deeper into this field, I can recommend you this paper. This was a joint work of GILA, NIST, and PDB people summarizing the development of the optical clocks until 2015. So here a bit more detail about the concept and idea of the single ion optical clock. The concept was developed already early on in the late 1970s by Hans Dehmelt, who had the seminal ideas in this field, and then people like David Wineland contributed a lot. There was the idea of the Paul trap that was essential for this of laser cooling. So an ion is trapped. This provides very long interaction times. In fact, we have trapped, these traps are deep. They are several electron volt deep. So in terms of thermal energy, this corresponds to 10,000s of kelvins. So they are stable against collisions. In fact, we trapped a single ytterbium ion in such a trap for more than a year. But with long interaction times here, I mean the time that we actually probe the reference transition with a laser, and this is now in the experiments a fraction of a second or a second. Fourier limited, this gives us like a Hertz line width. The trap provides the Lamb-Dicke confinement, so confinement within the wavelengths of the optical light. This comes just from the cooling and the trapping, and this is what reduces, what eliminates the Doppler shift on these transitions. And then, since we have to provide a signal just from a single ion, a double resonance scheme is used that was also proposed by Hans Dehmelt for this purpose. So think of this 3-level system where there is a ground state, then there is one resonance transition that is used for the cooling and for the fluorescence detection of the ion. So this is emitting the light that we are observing here with the camera. And then there is a very narrow reference transition to for the clock, and this is a metastable level. Say it has a lifetime of a second or so in order to provide a 1 Hertz line width. And now when one looks at the fluorescence light from a single particle in this under this condition, driving maybe both transitions simultaneously with 2 lasers, the signal looks like this. The electron basically can do either 2 things. Either it can oscillate on this transition, emitting fluorescence light, or it gets shelved into this metastable state, and then the ion turns dark. And this is an extremely efficient quantum amplification process. So basically you can say the absorption of 1 photon here prevents the subsequent scattering of a few million photons on this transition. And that is how this dark period really appears at a macroscopic signal, although it's really a single quantum event in a single atom. And this is of course spectroscopically very nice, because now for the operation of the clock we can count the rate of these dark periods as a function of the laser frequency that is used to drive this transition. And in this way very high resolution spectra can be obtained, very narrow spectra for long-lived transitions. But of course, since it is a single atom, there is still significant noise, the so-called quantum projection noise. So the measurement has to be repeated many times in order to obtain a spectrum. So these type of clocks is especially suitable if there is narrow transitions. So if by interrogating many times we get a very narrow spectrum, and then we get a strong slope here for the stabilization of a reference laser in the clock. The specific system that we are looking at, several ions are investigated around the world. The specific system that we are looking at is ytterbium plus, and it has a number of interesting specific advantages for this type of work. So all the transitions that are required for the cooling and for the reference can be derived from diode lasers. So this is a factor that makes this clock robust and reliable in the operation. We have in this isotope 171 that we work with, we have a nuclear spin of 1/2. That is very nice, very convenient, because the nuclear spin of 1/2 couples with the electrons with a single electron spin of 1/2. So there's a ground state with vanishing angular momentum that can be conveniently produced, and by hyperfine pumping. And then there is always integer angular momenta, so that there are transitions on the reference transitions that do not show any Zeeman effect. It has a large mass, which is interesting for the motion. So at a given temperature, the motion of the heavier atom is smaller than of a light atom. And maybe the most important feature for today for our clocks is that it does not only offer one, but actually two reference transitions, and these are shown here. So the outer valence electron can be excited from the ground state, which is a 6s state, to either a 5d state, so that changing the angular momentum by 2. It would be an electric quadrupole transition. And then there is another transition to a low-lying f state, where the angular momentum changes by 3 units, so an electric octupole transition. Octupole means higher forbidden, narrower than the quadrupole line. And what makes it interesting is really also the difference of the atomic structure, so of the electronic structure. So I've indicated here in the ground state, there is just a single 6s electron and the 4f shell is filled. And for the excitation on the quadrupole transition, the 6s electron gets promoted to 5d. So this is, the atom becomes a bigger, slightly higher excited, nothing happens to the core. The octupole is quite different. So here the 4f shell is opened, one of those electrons is excited, and now there is a hole inside this 4f shell, and this electron gets promoted so that the 6s shell is now filled with 2 electrons. It's spherically symmetric, and inside there is this hole in the 4f shell, which is, since it is the 4f shell, it's relatively close to the nucleus, and it is somewhat protected by this spherically symmetric outer 6s shell. And this leads to the interesting observation that these two transitions have really very different properties in terms of, first of all, of course, their line widths. The quadrupole about a 3 Hertz line width, the octupole much stronger forbidden nanohertz lines. We will never resolve this, of course, with a laser, but any improvement of laser of the laser line width we can use in making longer interrogations here. And then for the accuracy of the clock, it's very important that the sensitivity of these two transitions to external perturbations is very different. So for example, the quadrupole shift would be induced from electric field gradients from the outside, second order Zeeman shift. And since the structure here is quite different, the D state, the quadrupole, is much more sensitive than the F state, the octupole. And this gives us, there is a ratio like factors 20, 60 or so between these sensitivity coefficients. And it means we are doing the experiment with a single ion in a trap, and so we can use this quadrupole transition like an in situ diagnosis of these perturbations. And in this way, since we know these coefficients quite precisely, we have measured them, we can infer the corrections from these perturbations on the much more precise level on the octupole transition. And in this way, this clock is a little bit, we can say it corrects itself, so it gives us an information on its perturbations, and then we can use it to find the unperturbed correct frequency. And without going in further detail, so this is the uncertainty budget that exploiting this idea that we set up in 2016, we looked at a number of systematic effects, like there is effects from the remaining kinetic energy of the ion, so at the limit of the cooling there's still like a millikelvin temperature, so there's a small second order Doppler shift. The units here, so these two columns, this column here is the shift that we have to correct in the clock, and the second column is the uncertainty that we have. And both are given in units of 10⁻18 relative to the optical frequency. You can see the shifts are relatively small to start with. So this is the second order Doppler shift at a millikelvin temperature. It's about 4 parts in 10 to the minus 18. We have a relatively big uncertainty in how to determine it. So it's about 2 parts in 10 to the minus 18, the uncertainty we had at this stage. And then there's a number of other effects that are related to these field-induced shifts, like for example the blackbody radiation shift is an effect that comes from the effect that the ion is cold, but the apparatus around it is at room temperature. And the apparatus at room temperature, this means that the structure emits electric field, electric radiation, and it produces a Stark shift that we have to correct. So we have to know the temperature and of the apparatus and the homogeneity of the thermal environment. This is the biggest correction we have to apply. It's about 7 parts in 10 to the minus 17, and the uncertainty is about 2 parts in 10 to the minus 18. And then summing all these numbers up, this is what finally we do, we arrived at 3 parts in 10 to the minus 18 for the uncertainty. It's about 2 orders of magnitude lower than the uncertainty of the best cesium fountain clocks we have. At the time in 2016, this was the lowest uncertainty for a single ion clock. But the field is developing really now. There is another ion clock at NIST that has recently surpassed the 10 to the minus 18 threshold and is improving further. We are also working on improving this further, but what we did here at this stage was we asked ourselves, well, we should verify this. So this is an investigation of different shifts, and we have the sensitivity coefficients, and we infer the uncertainty. Can we really trust it? And the way to check it is to build 2 devices and to compare them. And so we built over time. You can see here a view of the big laboratory we call the clock hall at PTB. It is all the ensemble of clocks that we are operating in the department. So there's 2 cesium fountains here, and now you see already 3 generations of ytterbium clocks, and we see another one that we call optical clock. I will speak a little bit more. This is an industry cooperation project already. So now we compared the first 2 generations, ytterbium 1 and ytterbium 2. So we tried to in order to make this comparison meaningful, we did not make these systems rigorously identical, but we wanted really this as a test of how well can we control the systematic effects. So we used 2 different geometric constructions of ion traps, so that the electric fields are slightly different, that the thermal environment is slightly different. We used different interrogation times, different interrogation sequences, also different computer control. We were using one common laser, which is something that was very special, developed by colleagues at PTB, the group of Uwe Ster. This is a laser that is stabilized to a cryogenic silicon reference resonator for the short-term line widths, and it provides a very narrow line width, well below 1 Hertz. And this is a reference resonator that we use for interrogating the 2 ions. But then we had this laser master oscillator running it through two different acousto-optic modulators, so that we can independently tune the frequencies that we use to excite the 2 ions. And in this way we can directly, on a radio frequency, measure the difference between the 2 optical frequencies as seen by the ions. And we did this experiment now. We wanted to test the low 10⁻18 uncertainty. I've spoken about, we did this at a 1 Hertz resolution, given here by this interrogation time. 10⁻18 is a millihertz, so we needed to average for quite a long time. So we took data, and this is basically what you see, the problem of the quantum noise of just looking at a single particle. So we took data for several months in order to arrive at the point where the statistical uncertainty of this comparison was below what we expected as a systematic uncertainty. So here you can see the so-called Allan deviation. This is the instability of this frequency difference as a function of the averaging time. We started in the 10⁻15 range at about 1 second. And then it decreases like 1 over the square root of the averaging time We plotted this here to 1,000,000 seconds. 1,000,000 seconds, that's more than 10 days. It's like 2 weeks or so of averaging times. And we were really quite happy to see that the signal averages down quite nicely, like 1 over square root tau. And what we see here is really quantum noise, since we are doing the repeated and repeated state measurements of the single ion. And now you may ask for the final number. So all these points are measurements like over 10 minutes or so, and then the average of all the data, of all the numbers here, is this red line here, and under the magnifying glass you can see it is really very close to 0. So 0 would be the perfect agreement of the two optical frequencies in the two traps. And we saw an offset here of less than 2 millihertz within this gray area here, which is a 1 sigma uncertainty range for this comparison. So we were really happy. So we have found a relative frequency difference of 2.8 10⁻18 between the two clocks, and so well within the combined systematic uncertainty. So from this point of view, we could say it confirmed what we had estimated as a systematic uncertainty. Well, we took a lot of time now, and of course we would not have done it maybe, or our motivation was higher than this number. Of course, is very, very important, but we tried, can we do something else with this data? And there was a question from fundamental physics. We noticed that we could use it as something that may call a Michelson-Morley experiment for electrons, asking for violations of Lorentz invariance for an electronic transition. So you know the Michelson-Morley experiment, an interferometer with two arms at right angles, which is rotated, and it was done in the beginning of the last century, to see if there is a preferred direction for the speed of light. So if there would be testing the Ether hypothesis, is the speed of light really uniform in all directions as implied by Lorentz transformation? And here we are doing something similar, not for light, but for electrons. So for electrons, of course electrons can have any velocity up to the speed of light, but there is a dispersion relation. So between the energy of the electron and the speed of the electrons, there is a fixed relation, and the determining parameter is also the speed of light. So the speed of light is also the speed that determines this dispersion relation for the electron. And so one may ask the same question: is this speed of light that determines the dispersion relation for the electron, is it also homogeneous no matter how the electron is moving in space? So this was first proposed by the group of Hartmut Heffner in Berkeley. They did experiments with calcium ions and made first tests of this. And we noticed that we could do it significantly better with our ytterbium octopole clocks, because this F state of the excited state of this clock has a rather elongated electronic wave function. It's rather inhomogeneous, both in momentum and in position space. And so we can, this is the artist's conception, orienting the two different directions means the quantization axis of the two ions in the two traps, which we could select by the direction of the magnetic field that we can apply. We selected it at right angles, and then we could look, do we see a frequency difference between these two differently oriented ions as a function of the orientation of this whole apparatus in space. So we could think of turning it around, which of course we did not. We just left the stationary in the laboratory. But the laboratory, of course, is rotating together with Earth, and so by looking for a dependence on the orientation of Earth in space for the frequencies, we could say something about Lorentz invariance here. And it is exactly the same experiment, the same data I've shown you already now, but now we analyze them here in what people call a long periodogram. So we take the same data set and we look here at are there any periodicities inside. And we could start from something like a few minutes or so as a period up to 18 hours. And this is now, of course, a question of signal to noise. So the red lines here, so the blue is the experimental data that we obtained. The red lines here are giving the probabilities of finding in a uncorrelated, that is white noise data set of finding more than one peak. And so with 50%, the level would be here, and yes, there are 2 peaks or so, but if we say we ask for 2 sigma significance, the line would be here, and there is not a single peak anymore. So we can say there is no periodic signal at the 23.95 hours or at the 12 hours that we would expect for a dependence with the sidereal rotation of the Earth. And so from this, putting this together, we improved like a 100-fold improvement on these limits of violations of Lorentz invariance for electrons. And also we were quite happy. This graph, it looks white. So if one would worry maybe that there's a problem with the air conditioning in the laboratory that switches on and off at 1 hour or so, or there is nothing seen like this. We noticed for some times that the experiment was running overnight, and then the colleague that would be coming in the morning, the first person would look at the experiment and see and maybe tweak some knob here, and then we noticed after a few days we should stop this, we should not do it, because we would eventually implying a period of the daily period. Actually, but here we are looking actually for the position to the stars, and so the system is well behaved. And I think a nice example of how the clock improvements and fundamental physics goes together. So from these experiments, we have learned how we should improve the traps. So we are starting to build the next generation of clocks where we hope to reduce on these uncertainty contributions. Many of the uncertainties we had are actually related to the ion trap, to the motion of the ion in the trap, to the inhomogeneity of the trap environment. So we started to build a new clock where we hope to significantly reduce this uncertainty. And at this point also we obtained, now we come to quantum technology, no, maybe I should first briefly explain this here. So one aspect related to the trap is this effect of the blackbody radiation. So it is the electric field emitted by surfaces on the ion. Here you can see again pictures of the ion trap. We have an old generation, a new generation. This is the electrode structure. We apply like 1,000 volts or so alternating voltage, so if there are some losses then these structures heat up, and so we investigated this by taking thermal images and placing sensors and using improved materials. We are now building a trap where this heating effect is smaller, and if you remember the uncertainty budget, this was one of the biggest contributions that we had to the uncertainty. So we hope to be able to reduce this 1.8 uncertainty to less than 1. And now, so we worked on developing on further developments of our system, and at this stage we were contacted now in terms of quantum technology funding, and we were asked if it would be interesting to build now such a device together with industry, with the prospect of eventually building a device that could be used for users outside of a specialized metrology laboratory. So the idea here was to build like what one could call an autonomous or a push-button device of such a single ion clock. And so we joined forces with industries. You may know some of these names. There's Toptic, it's coordinated by Toptica, laser company. Menlo Systems is there, so it was funded by the German government, and total it's 6 companies and 2 research institutes, 2 universities, and the idea really to build a push-button device of such a single ion optical clock. We would not use this very narrow octopole transition, but for this type of device we would use a quadrupole transition. It's a bit easier to operate, and after a bit more than 2 years, you can see how the system looks like now. We have gone away from the optical tables. There's 2 racks. It's still relatively big, so it's not the clock that you like to carry along with you, but you may transport it, you may put it in a truck. We have one rack here where there is a more sensitive part of it, that is a laser oscillator, a reference cavity that's used for the stabilization. And here this part is you see from the outside a magnetically shielded box housing the ion trap, so this is a more sensitive part, and here's all the electronics and the computer control and everything, and that's needed for the operation. Here you can see how it's a very intense cooperation of the different companies, how they are cooperating to build the different parts. Our responsibility is mainly here, our expertise is the ion traps and what we call the physics package here inside. So you can see, again, working now with industry, with a vacuum company, you can mount this device on a 19-inch drawer to put it in a rack. The trap structure, you can see it's here. There's a transformer for the radio frequency field, a magnetic shielding that is still open. Here you see a closer view of the ion trap. It's a relatively big window, like 5 centimeters, in order so that we can have laser beams under different angles for the cooling and interrogation of the ion. The ion is held here in the center between the electrodes. There's a small source of the terbium metal for producing the ions, and all this is in the vacuum physics package. This is first characterizations of this device to show that it works. We used somewhat longer interrogation time, so the somewhat bigger line width. The target of this project is to build something that is significantly better than a hydrogen maser, which is a device that is the turnkey clock today, that is used in many national metrology institutes or at radio observatories for VLBI. And our target specification here was to be at least an order of magnitude better than at all interrogation times, at all in measurement times than a hydrogen maser. And even hydrogen masers at long time, so they show a drift, and our clock should also not show any drift. It should continue to average down. And here this was the first test that we did a few months ago of this new device against our stationary one. And this is well on the way. It's promising preliminary results, and I think it nicely shows how the technology goes in this. And I wanted to show it to you a little bit as a part of quantum technology development, and it's actually funded also by the European Quantum Technology Flagship. Okay, for the remaining 10 minutes or so, I would like to switch gears completely. Now again, back to basic research. I think Bill Phillips kindly mentioned it already at the end of his talk, that we have a new idea, and I'd like to share it with you. I think it's very interesting. It's in a very early stage of research, although it's going on for some time already. So we want to go away. We want to do something different from the atomic clock. We want to do the nuclear clock. So what do we mean by this? We mean that, again, there will be a laser, it will be an optical clock, there will be a laser stabilized to a reference transition. But in this case, the reference transition is not in the electron shell, like what I've spoken about so far, but it's inside the nucleus, often inside the nucleus, so that the oscillator would be stabilized to a nuclear or electromagnetic transition or to a gamma ray transition. And the motivation for this, there may be 3 reasons for this. The most important one maybe is the first one here, the higher precision. I've told you that the single ion ytterbium clock has to worry about these, for example, about the blackbody fields, the interaction with external electric fields. These electric fields, they deform the electron shell and change the frequencies a little bit. Now, if you go from the electron shell to the nucleus, the relevant charges, the protons are much more tightly bound in a much smaller region of space, so they are much less polarizable. They are not influenced by external fields. And this is what that we think that these field-induced shifts can be, that make a dominant contribution to the uncertainty budgets of the other optical clocks, can be dramatically reduced here. And this is something that is an important part of the motivation, again, towards the aim of the most precise clock. Another aspect is the higher stability, because this is something that is also, I think, is unique about the nuclear system. We are working with trapped ions now. People are working with ensembles of cold atoms and optical lasers with extremely dilute matter. Here, with a nuclear, in fact, one could consider to go into a solid state reference, because this is well established in nuclear physics, Mössbauer spectroscopy, that extremely narrow lines can be obtained even inside a solid. This is because of course, when the nuclei are assembled to the solid, the electronic level structure will be transferred into bands. There will be broad structures, but the nuclear resonances do not participate in this formation of the band, so the nuclei stay unperturbed. And so we could think of running, and with a small grain of salt, of running such a clock with maybe 10 to the 10 particles instead of the single or the 10,000 or 100,000 in a lattice clock. And the third one, you see I put it in lighter print here, it's not so relevant at present. We have seen that the development of the clocks has always gone towards higher frequencies, from mechanical clocks to microwave clocks to optical clocks. One could of course think of continuing this, of going maybe to X-rays or EUV, and which would be the domain of nuclear physics. So it could provide a higher stability, but at present we don't have the coherent narrow band radiation sources. So that's not an option. That's not an option right now, but that's really like an option for the future. But fortunately, nature prevents us with a system where we may investigate these ideas and disadvantages, because there is one transition where the energy is unusually low. It is not the 10-100 keV range of nuclear gamma ray transitions, but it is in the range of a few electron volts only, and more the optical energies. And this is a thorium-229 nucleus, a really special system from nuclear physics. So this summarizes what is known about this special nucleus. This is just a two-level system showing the nuclear ground state and the first nuclear excited state that people call an isomer. If it's a long-lived excited state, people call it the isomer. The two levels are separated by about 8 electron volts energy. The nuclear spin changes by one unit. It's a magnetic dipole transition. The lifetime is expected to be about 1,000 or maybe 10,000 seconds, so it would be a millihertz natural line widths, like in the also in the forbidden transitions of the shell. And here you see what else is known. Unfortunately, it's not a stable nucleus. It is undergoing alpha decay, so it has about an 8,000 years half-life. It's not a problem for the operation of the experiment, but it means you have to ask for permission to set up the experiment. We try to work with very small amounts of particles in an ion trap that works fine. So it's a bit difficult to obtain it. But and then this is the nuclear moments, the nuclear properties. So mu is the magnetic moment given in units of the nuclear magneton. You see 2,000 about proton to electron mass ratio smaller than the Bohr magneton. Normal units about 0.3. Quadrupole moment, this is the electric quadrupole moment. This shows that the charge distribution is not spherically symmetric. That's also common for electronic transitions. In electronic transitions, it would be the size of the atom, so 10 to the minus 10 meters squared times the charge. Here it's the size of the nucleus, so it's not 10 to the minus 10, but 10 to the minus 14 squared, 10 to the minus 28. You see, it's one of the examples where the nuclear moments are dramatically smaller. So this is the advantage of the nuclear clock, that the moments are smaller, but more important, it's that there is a choice of the electronic state for the interaction. That's actually the more important one. The more important criterion for getting rid of the systematic uncertainties. And explaining it in a very simple way here, if you consider now this, we want to drive this nuclear transition, but in an environment where there is an electronic shell. And so we have a two-level system, and here I've listed all the set of angular momentum quantum numbers. So we have some general quantum numbers, and we have electronic, orbital, spin angular momentum, total angular momentum. We have nuclear spin, and we have the total angular momentum. Now if we are driving this nuclear transition, the electronic part of the wave function stays unchanged. And this is the key idea. So it means that everything that couples to the electron shell, to the J and Ls quantum numbers, is to a very good approximation common mode in both states. So these effects would not change the frequency. Of course, the nuclear spin would change, and the overall total angular momentum would change. But this eliminates this not changing of the electronic degrees of freedom, eliminates a large class of the systematic shift that otherwise we would have to worry about. For example, the scalar quadratic Stark effects, the interaction with electric fields, which includes also collisions and the thermal radiation fields. So all these can be reduced drastically. If one looks at it in more detail, and there's two groups have done this. We published first this proposal in 2003, and this is a group of Alex Kuzmic, Andrei Debebianco. They generalized this further here in an analysis in 2012. One can show that what remains is really just differential effects, so-called hyperfine Stark shifts, and that this scheme eliminates the field-induced shifts to a level that is not achievable in any electronic atomic clock. So that looks like there would be a fundamental advantage for the nuclear clock. So the nuclear clock would look, it could work with a single ion, it could work with a solid, it could work with a single ion. One would again do something like this quantum jump observation. So there would be, think here, this is an electronic degree of freedom that would be used for laser cooling and fluorescence detection, and this is a nuclear degree of freedom. And now we can manipulate it. So here's the nucleus in the ground state, we have cooled the ion, and then the nucleus is driven to the other state. This changes the nuclear spin, it changes the hyperfine structure, and this is something that again we can easily read out via the electron shell. So we again have this quantum amplification mechanism for the operation of the clock. And this was actually part of the idea when we understood this, Christian Tammer and myself, that it would be very nice to transfer these ideas from the single ion clock to this nuclear transition. Now last year we have shown that this, just as a proof of principle of hyperfine structure, this is a hyperfine structure of several, like 1,000 thorium ions trapped. Most of them are in the nuclear ground state. You can see electronic transitions here in the nuclear ground state. And then the lines marked here in blue are the lines from the isomer that here was produced from a nuclear process, from an alpha decay of uranium. But here we did not yet excite this nucleus, but here we could show for the first time that we can resolve this hyperfine structure, like we will later do it in the clock. And we could also measure from this splitting the spectrum, we could measure the nuclear properties of the excited state. So the field is very much in development. So recently, it has been published, I think 2 weeks ago in Nature. Recently, there has been an improved measurement of the transition energy, not laser spectroscopy yet, but an electron spectroscopy experiment. Very important result, because the big problem, this actually is the biggest problem we have at present. There is a very narrow line, but we don't know the frequency very precisely, and we have to search it with a laser, and this will be very difficult. But once this has been obtained, I think it would be an extremely interesting system for the precise clock, also for these aspects of looking at possible violations of principles. Here one would also be sensitive not only to electronic effects, but also to nuclear effects, to the strong interaction. So it is a very hard problem experimentally, it seems, but now I think there is more than 10 groups working on it worldwide, so it could be very exciting, and people are really waiting for the breakthrough of exciting this nuclear transition for the laser with the first time. Okay, with this I'd like to conclude and to summarize. So I've spoken about the ytterbium clock with the two reference transitions and the nice agreement that we have obtained from the two clocks, how we have used it in a test of Lorentz invariance, that we are working towards usable quantum technology with a transportable optical clock, and that there is interesting new systems like nuclear clocks, highly charged ions. There is more interesting reference systems available. I'd like to thank my co-workers, the teams for the ytterbium and the thorium and the funding that we have available from different sources. And thank you for your attention.
Thank you, Professor. Questions?
Well, that was a lovely talk. I think I should explain why a number of us were laughing over here when you got to the point about making another clock. Because on Wednesday evening, a very young person asked, how do you know your clock is right? And I said, well, first you think of all the things that can make it go wrong and you calculate how much, but then you're never really sure, so you make another one. And it was almost as if we had colluded in, in our description. What I want to ask you is about the Lorentz invariance thing. Now, if I'm remembering correctly, when you do that kind of a test, the clock transition that you use has to be Zeeman sensitive because of... So would you say a little bit more about that?
Yes, sure. That was actually, oops, I need to go back through. That was a specialty of our experiment. It has to be sensitive to the orientation in space, and in many cases this is related to the Zeeman sensitivity. Or that was in the experiment that was done here by Hartmut Heffner's group in Berkeley. They had to combine it with the so the electron is oriented somehow. So and then the states normally are also Zeeman sensitive. This would be a big problem for the experiment because the magnetic field may be changing over the day. And they solved it by entangling two ions in a state that would still show a directional sensitivity but no Zeeman sensitivity. And our system was simpler, and this was what for us was also the idea for doing this experiment. So we did not have to do an entanglement between two ions. We took the entanglement, we received entanglement from free between the nucleus and the electron. And in this case, the MF0 component, although they are Zeeman insensitive from the overall symmetry, the electronic part of the wave function is not symmetric. So we have a state that had this orientational sensitivity for the electron, but no Zeeman sensitivity. And that was really a nice feature for our experiment.
So thank you very much for this wonderful talk. So I have a question and want to have a comment from you about so next the international community now is preparing things to change the definition of the second moment of time. So there exists a roadmap to change the definition of the second. So so it's big discussion what will be systems. And of course, PTV is one of the very good places making clocks with deuterium ion clock, and well, that will be a candidate to have a new definition of the second. So I would like to know your comments about possibilities to redefine the second. And the second part of my question is, well, now we have another player, which is nuclear clock, trolley. So it's time to order a clock. But so my question is, do you think this new approach to measure time to make clocks could play a role in the next redefinition of the second?
Well, I've spoken here mainly about two systems that was a complete personal choice, or I mean of our group, that these are the two favorite systems that we are working with. As you mentioned, there is a wide variety of different candidates for optical clocks that have individual advantages and problems maybe. I think that is what partly makes this field interesting, that there is really different systems with individual advantages and problems, and the research is progressing very rapidly, and it's always nearly nearly each year, I think it has changed which system actually provided the lower uncertainty, and it's going to continue for some time like this. I think scientifically it's a great situation because it shows the development in the field, and also again the aspect of comparing different systems. So if everybody would just working on one element, we may not be sure if there's something that we overlook with it, and that we should also compare the different species. So I think at the present stage, this will continue for quite some time, for several more years, I think. Now, from a more applied or management point of view, one may say, okay, but let's decide, let's select one and do the decision. I think that would be strongly justified if there would be applications waiting for it. So Bill Phillips explained yesterday how the situation for the electrical units, whether really the applications were waiting for the new definition. And for the unit of time, it's not the case. So telecommunication and navigation, they are very demanding, but they are happy with the 15 digits that we have from the Cesium. So I think we have a few more years to pursue this type of research and to really find a good system. Now, will the thorium be in this race already? I don't know. Maybe, maybe not. It will be. The thorium definitely will be a very interesting system for the scientific questions that we are asking. I think I think it's an open race now. I think one should make at some point do a selection. So we would need like a successor for Cesium. It should be one element. It should be one transition. There should be a consensus on this, and then people may still develop different clocks. What we have to do, we have Cesium clocks, we have rubidium clocks, we have hydrogen masers. Just the Cesium was selected for the definition. But it does not mean that we will not continue to use a variety of clocks. I think we will have a similar situation also for the optical clocks in the future.
So my question is about a discussion I had with Bill yesterday. If you manage to measure the energy of this gamma ray with very high precision, and then you measure the mass difference of the two isomers in a penning trap or something like that, do you think you would
the
have
mass difference? You mean
yes. Mm-hmm. Would you have access to measuring the mass in an alternative way and be competitive? What is your take? Will this be competitive to the current implementation?
We have been discussing this with, or we have been discussing if it would be an option that would improve on the gamma spectroscopy. It could, yes, it could in principle, yes, but as far as I know, nobody has started such an experiment so far, because what would be the problem? It also requires relatively long measurement times and the lifetime, so the isomer would have to be trapped in a penning trap, so one would have to install a small radioactive source to produce the isomer, and then it would have a lifetime of maybe 1 hour or so, and then so these are completely purely technical considerations. I think that people that are working on this type of devices are saying, no, we are not really so interested in doing it. But maybe if the search continues like for another few years or so without much improvement, maybe then it could be a nice and interesting option. Yes.
Okay, so I think it's a good moment to stop. Let's thank the speaker again.